a look at example 5.119. So it says a small bead can slide without friction on a circular hoop that is in a vertical plane that has a radius of 0.1 meters. The hoop rotates at a constant rate of 4 revolutions per second about a vertical diameter. Find the angle at which the bead is in vertical equilibrium. Of course, there's radial acceleration, so there is acceleration in the radial direction, just not in the vertical one. Part B wants to know, is it possible for the bead to ride at the same elevation as the center? So could I get it to like ride right here or right here? And then C, what will happen if the hoop rotates at 1 revolution per second? So if I slow down the hoop, what happens to the angle at which that bead is sitting? Okay. So let's start out with a free body diagram, since they did say they wanted in vertical equilibrium. So let's think about the forces acting on this here. So we got gravity, mg, and the bead is sitting on this hoop, so there is a normal force perpendicular to the hoop's edge. They also hinted that there was a centripetal acceleration. So we're going to have to go ahead and find this r value here. And we want to identify this direction as AC and label it as positive. This R value here is going to be 0.1 times the sine of my angle, since this here is the radius of 0.1 meters. Okay, let's kind of figure this out a little bit more. So I'm going to have to create and resolve this normal force into components. This angle here is the same as that angle there. So we end up with normal force cosine of theta here, normal force sine of theta there. All right, let's generate some equations, shall we? So the sum of the forces in the y direction should be 0, and the sum of the forces parallel to the radius should be causing MAC. Now the reason we need this one is inside of AC is v squared over r, and the reason we need that is inside of v is going to be our frequency. Now usually we do 2 pi r divided by the period, but instead of doing 1 over period, I can just put in frequency. All right, so that's how our frequency is going to get into our system of equations here. So I have normal force cosine of theta minus mg equals 0 here, and then over here I have inward my positive direction, n sine theta equals m times, what do we got? 4 pi squared r, which is 0.1 sine theta, frequency squared. We got a whole bunch of variables we don't know and we don't want in here. So I see an m and an m, I see an n and an n. So let's start by trying to get rid of those. So if I solve for n over here, I get mg divided by the cosine of theta. I can make that substitution over here. So I have mg sine theta divided by the cosine of theta equals m times 4 pi squared times 0.1 sine of theta times frequency squared. All right, so got rid of the normal force. I can also get rid of the m's now. Also, there's a sine of theta that's going to cancel out for me, so we don't need that sine of theta. And our goal here is to solve for theta. So let's see if we can isolate this cosine. So I have g divided by 4 pi squared times 0.1 times frequency squared equals cosine of theta. Go ahead, take the inverse cosine here. So I have theta is equal to the inverse cosine of 9.8 divided by 4 pi squared times 0.1 times 4 squared. If we plug this into our calculator, we find out that we get an angle of 81 degrees. So it's darn near up to that midpoint spot, but not quite there. And so then part B says, well, can it get there? Well, that is a good question. Can it get there? Can we get 90 degrees? Well, if we think, what's the cosine of 90 degrees? The cosine of 90 degrees is 0. Can we ever make this 0? No, you can't make this 0. Now it's a limit, right? Because as the frequency approaches infinity, this approaches 0, but it can't ever get there. So we can't ride right at that spot level with the center of the hoop. Part C takes this the other direction, says, well, let's slow it down a little bit. Now, I'd like you to try this on your calculator for me. Instead of putting in a 4 there, go ahead and put a 1 in. Take a second to do that. All right, so you took a second, you put in 1 here. What'd you get? Domain error. What could that possibly mean? Okay, so there's a limit. There's a certain range that this works for. So on the other end of the spectrum, so we can't have a 0 here, but what if I take and I say, well, what's the slowest? What if it's way down here? What revolution per minute is that? Or revolution per second is that? So the cosine function can get down to as low as 1. Okay, now there is a slight problem because of these sine angles here, but we're gonna ignore that because they cross out, but they're zeros at that point. So the cosine function, so if I plug in 1 here and solve for the frequency, we find out that the frequency is 1.58 revolutions per second, which means anything less than that, it's not going to go up the side. It's going to stay down there. Now we're assuming these are point masses, and we're kind of working with this equation the way it is. So we do have some issues, but 1 doesn't work for our equation. So that's why we got a domain error when we did that. There you go.